And when visiting photo festivals or other occasions and showing our prints to gallery directors, curators, and other artists, commercial representatives, and so on, I might be tempted to print my images on a tough as nails, though not overly fluorescent, resin-coated commercial paper. Because though my prints will be handled over and over again in these fast and furious consultations, they will still look as good at the end of the day as they did at the start of the day, thanks to the robust characteristics of this commercial paper. The trade-off, though, is that our prints on these inexpensive commercial papers will appear a little flatter and duller, dead on arrival, compared to how they will look on a brighter photographic paper or beautiful mould-made fine art paper, such as those from Arches in France. All right, so there's a few additional practical, real-world distinctions to consider to help us judge and balance those aesthetic advantages that we've been attributing to the different papers we've been investigating, such as cool tones receding, warm tones advancing, and so on, with their physical and their practical attribute. And there are even more pictorial considerations that we can include in these evaluations. For example, here's a comparison between the density range or exposure scale of two classic papers. My beloved Canson Platine fiber rag with its exceptionally beautiful, soft, semi-gloss surface, and the largest gamut, the blackest blacks, the greatest presence and dimensionality of any paper I've ever experienced, compared with Canson Infinity's Rag Photographique, a beautiful, smooth, matte-surfaced, classic fine art paper. Now, I'm measuring reflective density here, just like in the darkroom. And remember, these are log to the base 10 densities. So dividing the density by 0.3, which is the equivalent of one exposure value, or one f-stop in photography, determines its exposure scale. Now, the paper white, or D-min of these papers, is exceptional. Printing the maximum amount of black ink my printer's beautiful Epson Ultrachrome Pro ink set can apply, and then measuring the result with my spectrodensitometer quantifies the huge visual difference between the maximum black on each paper. We can determine the paper's contrast ratio or exposure scale by then calculating the antilog of the density difference between papers D-min and D-max. I used my OS calculator to do this, where Platine fiber rag has an exposure scale of 200 to 1. That means the paper white is 200 times brighter than the blackest black. On the other hand, my beautiful matte-surfaced Rag Photographique fine art paper is only 45 times brighter than its blackest black. And some of the poorer quality art papers can have an exposure scale of only 30 to 1 or even less, and therefore can appear terribly flat, awfully dull, and dead on arrival. Yet on the matte-surfaced Rag Photographique, I'm actually printing with Epson's matte black ink, which is an even denser black pigment ink than the photo black ink we're printing with on the soft gloss encapsulating surface of Platine fiber rag. So I'm actually using a black ink on the matte surface, but it ends up appearing much less so. Much less so because compared with the glossy Platine surface, the matte surface is scattering so much more of the incident light falling on it, that is, before it gets transmitted and absorbed by the underlying black pigment. And therefore, on the matte surface, it appears significantly less dark. I guess similar to how receding mountain ranges appear less dark through increasing atmospheric haze. Now, solutions to this contradiction of printing on matte surfaces, we're going to need to investigate this later today when we're preparing our files for printing, including ways that we can best edit and adapt our images for printing on these beautiful matte-surfaced fine art media. That is, without our images ending up looking flat, muddy, unresponsive, and inconsequential, despite the physical beauty of the fine art paper itself that they're being printed on. Also, we are not yet looking at transmissive densities, but we will definitely be referring to this later in the workshop, where we also need to look at our monitor calibration standards and monitor settings, especially for those of you who were earlier on asking about soft proofing and correlating print-to-screen values for different outputs. But at the moment, I'm just considering the physics behind how our beautiful printing papers and their unique surface characteristics change the appearance of our images on them, and therefore also our aesthetic judgments about them. Now, there is another critical distinction in the selection of our printing papers and their application, which is the amount of fluorescence different papers exhibit when viewed under different lighting conditions. There's a metric we call the virtual fluorescence standard, which is how we can quantify the amount of optical brightening agents and their potential fluorescence for different printing papers. For example, look at my measurements of Canson photoluster when it is exposed to illumination rich in ultraviolet radiation, such as the D65 daylight standard. Now, photoluster actually ends up reflecting way more than 100% of the light illuminating it, but only when its OBA content is excited by incident UV radiation, where in proportion to its OBA content and the level of excitation, it also ends up making our images appear cold and bluish, and hence we call these cold-toned papers. But it gets worse, because our images printed on highly fluorescent papers, like photoluster, will also radically change their appearance when viewed under different light spectra, where they'll appear to oscillate between a dull blue coldness and an ugly yellow-green flatness at their extremes, that is, depending on the lighting conditions they're being viewed under. And only under specific illumination will they appear neutral and alive, that is, the specific illumination they are balanced to. Now, on the other hand, when our images are printed on higher quality papers like Platine fiber rag or rag photographique that contain zero OBA and therefore emit zero fluorescence under any lighting conditions, our images will then appear vastly more consistent, more predictable, and therefore our aesthetic judgments about them also won't become confused or corrupted when viewing our prints under a wide range of different lighting and viewing conditions. Now, we've got to examine all of this again much later in the workshop and in much greater detail, especially when we come to set up and standardize our own print viewing and print evaluating environments. I mean, I can hardly wait. But for now,